Certain molecules mix with water to produce acids. These molecules are primarily carbon dioxide and the oxides of sulfur and nitrogen. The source of these molecules is the combustion of fossil fuels, primarily coal. Now, coal has been burned for a long time, and we've known acid rain since we've been burning coal. Coal may not be making headlines as much anymore, but it's kind of like a bad penny. It keeps coming back to haunt us. So if you see this headline, this is from 1980, and it talks about acid rain hurting the neighbors. Acid rain is a regional phenomenon. We may produce it here. In Ohio, we produce it in the coal-burning power plants primarily. It is a product of the coal-burning power plants. But the prevailing winds sweep it eastward. As it says here, it was noted in 1852, and they used to burn coal for heat. Oh, they produce it, especially in urban areas such as London, that horrible fog, which was it would be like fog, which is just water vapor mixed with these oxides of primarily sulfur, creating a very thick, very noxious fumes. Also very opaque. If you remember, Jack the Ripper was able to move in and out of them very easily. It was left now, people started talking about it again, excuse me, in 1950s, and we've seen it come and go, but in the 1980s, it really became a cause de célèbre for the media, and we got to see a lot of denuded trees, dead fish, and other very visual manifestations of the problem. Acid rain problem was compounded by an attempt to fix another problem, that is local pollution, or local pollution. They made the exhaust towers, the smokestacks, taller so that people would not be breathing, the neighbors would not be breathing the combustion products. Well, that's only put the fumes up higher into close to the stratosphere. Okay. All right, we'll get back to exactly what acid rain is and what it's done, but let's first talk about acids. We're all familiar with acids. You cannot go through a day without interacting with an acid. Acids conjure up images of destruction, corrosion, but in truth, they're very necessary. Acids are very common. Vinegar, citric acid, malic acid, lactic acid, phosphoric acid. They have a sour taste. Right. And they are corrosive to many metals. But they are everywhere. I guess I want to emphasize that. Almost in all food, even meat has a little bit of acid in it because acids impede bacterial growth. Okay. Now, acids are substances that release hydrogen ions. That's what this is, H+. Can you notice for a second, this is a bare naked proton. If we look at the hydrogen atom, he has one proton, that's his atomic number, and no neutrons. So his atomic mass number is the same. So if we take away an electron, thus making him positive, his one electron, he simply is a proton. We write it as an H, but we could write it as simply P+. Okay, so acids are substances that release hydrogen ions when you put them in water. And we can write it like this. For one of the most common acids is hydrochloric acid. This is the stuff that's in your tummy that breaks down your food. All right, and this will ionize or break into its ions, dissociate is the technical name, into a H plus and a Cl minus. Now here's our player. This is the one who does all the chemical work. This is pretty much just a spectator. How do we recognize acids? When we see an acid, usually the chemical formula begins with an H. And if you recall, we talked about the fact that you can write chemical formulas different ways. You can write a chemical different ways. You can use balls for the atoms. You can use lines for the bonds. And often when we write the chemical formula, we will write it in such a way to emphasize its behavior, its chemical behavior. So here is nitric acid, and it's written like this even though the hydrogen is not attached to the nitrogen. It is attached to one of those oxygens here. That's not really that important for us, but I just want you to be able to realize that H is a leader. Remember water? This is kind of an exception in a way, although water will act as an acid. Acts at times like an acid. Water is so lovely and unique. He also acts like a base when he needs it. Needs to be. So he is amphoteric, meaning he goes both ways. Okay. All right. Now, what are bases? It's kind of like love and marriage. If you've got a reaction, one guy will act like an acid and the other guy will act like a base if you open up your definition of bases. But for us, the bases will simply be any compound that produces hydroxide in water. All right. Because sometimes, you got to say in water, because sometimes it doesn't bring its hydroxide, the OH minus with it, it takes it, it forces it from water. So here's a very common one. This is Li, sodium hydroxide. She breaks up into her ions too when you put them in water. Right. Up here I forgot to write water too. You write it over the arrow to show that it's not chemically reacting. You can also simply put it as a subscript here. The AQ means aqueous. Aqueous. It just so happens this is a gas and this is a solid. All right. So here's our player for a base. But the reason why we have to sometimes be explicit to say we have water in there, because here he is going to chemically react with water. I'm just underlining it. That has no other significance. This is ammonia. And what ammonia will do is, or what water will act as the acid and donate an H plus to ammonia to make it NH4 plus. And look who my other friend is, popping off that OH minus. So one of the H pluses goes over here from water, and we end up with an increase in OH minus. Good enough. Now bases we don't see very much. These feel slippery. They are bitter. Not that you taste these very much, but I mean, if you've ever had your mother wipe your mouth out with soap, this is where we see them mostly, is in soaps. You've got to be careful too, because you don't want to go to very high concentration of them. For example, this lye in drain openers, because it denatures proteins. It will break down the overall structures of the protein in your fingers. That's what makes it slippery. So, all right. What would we say is a good way to measure the content of this OH minus and H plus in the water? First, we need to talk about something called the mole. The mole is simply a convenient unit for an enormous collection of anything. This concept isn't new. Think about a dozen. A dozen, the word dozen means a collection of 12. A ream, 144 sheets? Ooh, I can't remember. But oh no, gross is 144. I'm sorry. but it just simply means a collection. Well, 12 atoms is nothing, but 6.022 times 10 to the 23rd is enough to really have something we can work with. Okay. Remember that this simply means 6 with 23 zeros after it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Bing, bing, bing. Oh my gosh. That's a very big number. All right, now this number is called Avogadro's number, and it is simply 6.022 times 10 to the 23rd objects is Avogadro's number. And Avogadro's number equals 1 mole. Alrighty. So a mole of anything, a mole of baseballs is 6.022 times 10 to the 23rd. A mole of water molecules is that many. A mole of sodium atoms is that many. Mole of balls is that many. All right, great. Okay. Now let's look at the periodic table for a second, and we can see that the elements are all listed up there. We've talked about, here's the 1 to 2 letter symbol. In this case, it's going to be carbon. Here's the atomic number. Remember, this is the number of protons and electrons if it's a neutral atom. The molar mass is what we are concentrating on here. It is telling us that 1 mole of this element, in this case carbon, remember he's carbon, weighs 12.01 grams. This is numerically equal to the mass of 1 atom of carbon in atomic mass units. They both use carbon as a standard, so they're numerically the same. Now, chemists are not very inventive sometimes, so the molar mass is what they call it, and it is simply the mass of a mole. Right? So the molar mass equals the mass of a mole. Okay. All right, let's see how we can use this. What we can do is figure out if you have certain mass of carbon, let's say 36.03 grams, which is probably like a half a cup if you had graphite. How many moles is that? This is telling me how many particles. This is units of particles. Units of atoms, or let's just say particles in general. So I've gone from a mass, that's grams, to a number, units over here. How many moles is that? Well, we first can write down the amount that we're given, and I'm going to use grams of carbon. All right. And I'll use this molar mass as my conversion factor. Here's my conversion factor. Do you remember we talked about conversion factors, that they can be used 2 ways. They can either convert from one set of units to another, that is, for example, English units to the metric units, or they can relate properties. Density. Density relates mass of something to its volume. So if I had the same volume of lead and feathers, they would weigh vastly different amounts. Right? In this case, we're going to relate to how many grams of carbon in 1 mole. This is my molar mass. This is my conversion factor. And when I do the math, do the calculations with the numbers, plus evaluate the units, I end up with 3.0 moles of carbon. Notice I can cancel out those units, grams carbon, and I end up with mole carbon, 3 moles of carbon. Right? I can also find out how many atoms that would be by using another conversion factor, Avogadro's number. The definition of a mole is the conversion factor relating, let me do it up here, relating mass to moles. And here we're going to use Avogadro's number to relate moles to number of atoms. I know that 1 mole of carbon atoms, or I can just write carbon, is equivalent to 6.022 times 10 to the 23rd atoms. By definition, like if this was dozen, I could put 1 dozen down here is equivalent to 12 atoms. This is my conversion factor relating the term mole to number of atoms. And I end up with atoms, and the moles of carbon cancels out. I do the math portion, and I end up with 1.8 times 10 to the 24th atoms of carbon.